Welcome back to microeconomics. My name is Keith Akucha, and in this video, we're going through a bunch of game theory examples. This is Unit 4 from the core textbook. We got about 10 different examples to work through, so some of them are just game matrices, others are a bit more to deal with altruism and the indifference curves that go with that. And really where I want to start off, though, is not just going through examples, but rather getting into the definitional side, taking a look at just making sure we're on the same page about what we mean by the Pareto criterion and Pareto efficiency. And with that, we kind of set ourselves up for evaluating an example at least. So let's go jump over, take a look at that, and then we will work through each of the subsequent examples in turn. Okay, so here we have a situation out of the textbook. This is taking a look at the payoffs between Anil and Bala for whether or not they use the IPC, that's the Integrated Pest Control, or the Toxic Tide. Now, in this case here, we have a series of different payoffs, and they've just shortened those payoffs there based off of TT for toxic tide, toxic tide. That would be this outcome. Let me switch to laser pointer. There we go. That would be this outcome here, TT, 2, 2, or IT, that's Bala choosing IPC and Anil choosing toxic tide. Sorry, other way around. There we go. And that would be IT. And on and on. So we have 4 different payoffs listed because we have 4 different payoffs in our matrix. Okay, but what exactly do we mean in terms of our Pareto criterion, and what do we mean by Pareto efficiency? Well, first, the Pareto criterion. I'm just going to read this as it is there. According to the Pareto criterion, allocation A, there's no A on here, it's just referring to some allocation A, is better than allocation B if at least one party would be strictly better off with A than B, and nobody would be worse off. So another way that we could say that is that if we could move to another outcome such that nobody is worse off in that transition and at least one person is strictly better off. And I can make a point like that here on this diagram to showcase that. I really want you to keep in mind that point does not exist in this payoff matrix. It is entirely just for demonstration. So let's say that we have, let's just drag up a point here from 2, something like that. Well, let's throw in a point right here. So if we were to throw in a point right there, that would be at payoff of 2, 3. Well, at 2, 3, what we see is that Anil is no worse off, but Bala is going to be better off. So in that case there, we would say that we would prefer this one. The allocation, we can say that this would be allocation A to allocation B, and we would prefer allocation A to B because, hey, one person is better off and no one is worse off in this scenario. So that is, we would say that that A, Pareto dominates B, or that A would be a Pareto improvement over B. We are doing better. Okay, let's just clean this up here. We can then get to the second set of definitions, that is this bit here over here on the right, which is taking a look at Pareto efficiency. And again, just to read that off, an allocation that is not Pareto dominated by any other allocation is described as Pareto efficient. So the only definition here is that it's not dominated. We can have a Pareto efficient outcome as long as it's not dominated. If an allocation is Pareto efficient, then there is no alternative allocation in which at least one party would be made better off and nobody worse off. Okay, well, let's take a look at this. Let's walk through, talk through it, and see where we're at. What I want to do, let's start off with red, and we'll start off with this point here. So if we just do a vertical line and a horizontal line, anything that would be touching the vertical or touching the horizontal or up to the right of it would be Pareto dominated by IT. In the same way where we just created that point A just north of TT there, well, that was Pareto dominated TT because it allowed one person to be better off with no one being worse off. So if we do that for each of these, what we can see is that when we are looking with respect to TT, this outcome here, II, well, II Pareto dominates TT. That is, we would always prefer this to that because both are better off. We're getting more payoff at II than we are at TT. So that is, in this case here, TT would be Pareto inefficient because it's been dominated by II. The final one here, what do we have? TI. Let's actually use the line tool there, make that actually a straight line. There we go. So based off of this definition then, an allocation that is not Pareto dominated by any other allocation is described as Pareto efficient. So in this case here, our Pareto efficient outcomes are TI, R, IT, and then finally the last one is II. And you're like, Keith, well, why didn't you draw any lines coming off of II? Well, I could. There's just absolutely nothing up to the right. And it's because II has Pareto dominated TT. So we would prefer that one. We have 3 Pareto efficient outcomes in this case, keeping in mind that in order to switch from one to another, we might win overall as society, that is, as everybody involved, but you can't move from one to the other without somebody being worse off. And so that's why we have 3 Pareto efficient outcomes and then one Pareto inefficient outcome. This guy here, TT, that was Pareto inefficient. Let's quickly talk about this whole bit about the trade-offs here between them. So let's say that we wanted to move from IT. So IT, that would be payoff of 1, comma 4. If we wanted, we could kind of say, hey, altogether that social payoff is 1 to Anil, 4 to Bala. We're getting 5 total social payoff, whatever that means. Maybe that's in terms of dollars. If we go to II, we are getting a payoff of 3, comma 3. So in this case here, the total social payoff is 6. But let's keep in mind why both of these are Pareto efficient. We cannot move from IT to II without somebody being worse off. And in this case here, if we were to make that move, Bala would be required to give up, sorry, I was about to write 3. Bala is required to give up 1 in order for Anil to gain 2. So in this case here, yeah, Anil is strictly better off. That part is satisfied. But Bala is worse off. She has been harmed, has been hurt in this process, and so not a Pareto improvement. Even though total social increases. And that's one of the big things that I really want you to be able to take away from this is that we can have an increase in social welfare, but be stuck at another Pareto efficient outcome such that there is no way to have a Pareto improvement because somebody gets hurt in that process of moving. You will see some situations where they will call this state here, moving from IT to II, as a potential Pareto improvement. And the reason why we'd call it a potential Pareto improvement is because there is the potential for Anil, right? Anil's getting +2, and Neil could compensate Bala, give Bala one of those, and make Bala no worse off. In which case, there is the potential for a Pareto improvement. But that does depend on reallocation of payoffs as we move from one to the next. Okay, that went through a bit of the parts to do with Pareto efficiency, Pareto improvements, and that new term that I threw in there, potential Pareto improvements. But what I want to go to now is actually looking at playing these games. That is, we have that matrix here. We haven't even looked at how we play the game. Let's go jump over, look at a bunch of different questions, examples, and talk through how we do that. Let's read through the question here. So we have Anna and Brian are discussing what to watch on the TV tonight. There are two choices. They can either watch a movie, a film, or the Snooker World Championships. That sounds riveting. They can either watch one of the two programs together, or they separate and they watch different programs in separate rooms. The following table represents the payoffs of Anna and Brian, depending on their choice of program. The first number is Anna's payoffs, where the second number is Brian's payoffs. That's the very typical way that we would denote this, is the first set of payoffs would be what we'd call the row player. The second set of payoffs would be the column player. Based on this information, read the following statements and select the correct ones. Okay, before we even go and work through this, I want to just talk through how we play these games. And that is the way that we do this. What we are looking for is we are looking for the best response. So the idea being is I don't know what you're going to do, but if you do something, what is my best response to that? And then if you do something else, what is my best response to that? And we can then evaluate to see where our best responses fall. And ultimately, we end up with what we would call a Nash equilibrium. Nash equilibrium. And a Nash equilibrium takes place wherever we have overlapping best responses. What I want to be clear is that depending on the game, we can have no overlapping best responses. That is, they never play the same one. They never end up at a stable outcome. We could have one Nash equilibrium, that is one case with overlapping best responses, or we could have several overlapping best responses. It's not necessarily unique. Nash equilibrium is just where we have overlapping best responses. Okay, so how do we play this game? Well, we're going to start. We just pick a player to start with. Doesn't matter which one you pick. I'm going to pick the row player. I'm going to pick Anna. And the way that we do that is we say, okay, Anna is going to presume that Brian is definitely going for snooker. If Brian is definitely going for snooker, Anna, oh my goodness, Anna then wants to figure out what her best response is. And she has the option of either getting a payoff of 2 or a payoff of 5. Between those two, 5 is the better payoff, so Anna would choose snooker as well. That's a little bit too dark there. Let's try that again, see if I can get that a little bit lighter. There we go. We can still kind of see the 5. Now we know what Anna's best response is to Brian choosing snooker. But what does Anna do if Brian chooses film? So we just go and continue. We now say, hey, now for sure Brian is choosing film. What is Anna's best response to film? Either a payoff of 1 or a payoff of 4. 4 is the better payoff in that case there. So if Brian chooses film, Anna chooses film. If Brian chooses snooker, Anna chooses snooker. What we would say in this case here is that Anna does not have a dominant strategy. A dominant strategy would be a strategy that you always play, irrespective of what your opponent, the other game player, chooses. Seems weird to refer to Anna and Brian, whom I'm assuming are a couple, as opponents, but in this case, that's how we view it. Okay, so we now know what Anna's best responses are. Let's turn the table around and let's now play as Brian. So if we are playing as Brian, I'm going to use green for Brian. We do the same thing. We say, okay, for Brian, Brian is going to assume that Anna chooses snooker. Then Brian is going to say, well, what's my best response if she chooses snooker? And Brian can have a payoff of 8 or a payoff of 2. Payoff of 8 sounds better. So if Anna chooses snooker, Brian's best response is snooker. What if Anna chooses film, though? Well, if Anna chooses film, then Brian is picking between 6 and 4. We see here that Brian has the incentive to choose snooker again. Better payoff. In this case, what we see is that Brian, irrespective of what Anna chooses, Brian is always picking snooker. So we would say that Brian does have a dominant strategy. Brian's dominant strategy is to always watch snooker. So Brian has a dominant strategy of snooker. And look at this right here. We have overlapping best responses. That is both of the best responses in the same cell. And that is at the outcome, snooker, snooker. Okay. So taking a look at our comments, which one is the correct one? Well, first off, Brian's dominant strategy is to watch snooker. We've already identified that. No matter what Anna does, Brian's always getting the better payoffs from snooker. So yes, that is true. Anna's dominant strategy is to watch the film. No, Anna just wants to do what Brian does. Anna does not have a dominant strategy. Anna's result varies based off of what Brian chooses. So no dominant strategy there. The dominant strategy equilibrium is for both to watch snooker. This is a little bit tricky. In this case here, it says the dominant strategy equilibrium. This is where we would have overlapping dominant strategies. And it doesn't have a dominant strategy. So there is no dominant strategy equilibrium. We do have our Nash equilibrium. That is where we have overlapping best responses, but that is not a dominant strategy equilibrium. So that's a false statement. Finally, there is no dominant strategy equilibrium. Yeah, that there has to be true. There is no dominant strategy equilibrium because Anna doesn't have a dominant strategy. So because Anna doesn't have a dominant strategy, we cannot have a dominant strategy equilibrium. Okay, that's our first game. Let's go jump over. Let's take a look at another one and see where that works out. Okay, in this one, we just have a series of indifference curves, and I believe we're just asking a bunch of questions and interpreting them. So what I want to do is, this is the first time we've kind of seen it. I want to explain what each of these A, B, C, and D indifference curves really mean altogether, and then we'll take a look at the potential correct comments. Let's maybe read the read-in first. So the following figure depicts possible indifference curves of Alan, whose utility depends on his and or his friend Beatrice's levels of consumption. Alan's consumption is along the horizontal axis, where Beatrice's consumption is along the vertical axis. Well, let's read the following statements about the curves A through D and select the correct ones. Okay, so these are indifference curves. Again, what these are saying is the rate in which I am indifferent, that is having some static, steady happiness, irrespective of where I move along these curves. So let's start off with A. If we are taking a look at A, so this is the green line there, vertical, what this is saying is that Alan's happiness is here, unchanging, at some fixed level of Alan's consumption. That is, Beatrice changes her consumption, maybe goes all the way to infinite consumption, or Beatrice consumes 0. In all of those possible cases, from Beatrice going to infinity to 0, Alan's happiness is unchanged. It is vertical. That is, Alan's happiness does not depend on Beatrice's consumption. We would say that Alan is entirely selfish in this case. Alan's utility, Alan's happiness, only comes from Alan's consumption. So A, we only care about Alan's consumption for Alan. B, we have a horizontal line. Again, these are the indifference curves of Alan. This is the important thing to keep in mind. These are all Alan's happiness, where Alan is indifferent. In this case, for B, being horizontal, it's the complete opposite situation. Alan is amazingly altruistic in this case, such that Alan's happiness depends only on Beatrice's consumption. When Beatrice has this level of consumption, then Alan has this level of happiness, that utility. And what we notice is if Alan consumes more, there's no trade-off, there's no change, there's no rate in which gives up Beatrice's consumption for his own. So in this case, B, Alan is entirely ridiculously altruistic, only cares about Beatrice's consumption and well-being. His own does not play into his utility function, does not play into his preferences or his indifference curves. What do we have for C? Here we're looking at the blue line. So in the case of C, we have trade-off taking place here, right? We'd have some marginal rate of transformation as Alan, this is a indifference curve. This would be some marginal rate of substitution, as in order to maintain Alan's happiness, Alan would be willing to forego some of his own consumption if that meant Beatrice's consumption were to increase. So that is, Alan is altruistic to a degree, but still values his own consumption as well. It's not entirely only Beatrice that Alan cares about. It is, hey, Alan cares about Alan, but gets some benefit seeing his friend being well off as well. D, we get this funny kind of like hard right angle here. What this is telling us is, hey, we just have whoever has the least amount of consumption, that gives us our indifference curve. And that is, hey, if Beatrice's consumption is at that low point there, well, then we have the indifference curve going off that way. Alan could increase consumption, increase consumption, increase consumption. It does nothing to Alan's well-being because Alan is concerned about Beatrice's minimum. Similarly, Beatrice could increase consumption, increase consumption, increase consumption, and that does nothing for Alan's happiness because Alan's happiness is being determined by the minimum of Alan's consumption. So in this case here, whatever the minimum of the consumption is for whichever one of them determines the level of happiness that Alan gets. Great. So we've explained these 4 different types of indifference curves and how we would interpret them, what they mean. Let's now see which of these statements are true. Indifference curve A. Alan only cares about Beatrice's consumption level. No, we just said when we went through this that A was Alan only cares about Alan's consumption. Whatever Beatrice does, shoots off to infinity consumption, shoots down to 0 consumption, has 0 impact on Alan's happiness. Alan does not care. So that is false. Indifference curve B, Alan only cares about the sum of his and Beatrice's consumption. Well, no. In B, this is Alan only cares about Beatrice's consumption. Alan does not care about his own consumption. So the statement, Alan only cares about the sum of them, that would be probably more similar to C there. But no, B is that Alan only cares about Beatrice's consumption. Indifference curve C, Alan only cares about his consumption. Nope, we said that was A. C is that Alan cares about both of them. D, Alan's utility is derived from the minimum of his and Beatrice's consumption levels. Hey, when I said, what exactly does this mean? That is exactly how I just explained D. So in this case here, D is our one and only correct answer. Hopefully that helped us in interpreting these indifference curves, the difference between them. Again, vertical would be completely selfish. You only care about you. Horizontal would be ridiculously altruistic. You only care about the other person. You don't care about you at all. Some downward slope in between those two extremes You have a level of altruism where you care about both you and the other person. And then you get that hard right angle, and you don't care about where you end up with consumption. Your happiness is determined by the minimum consumption from one of you. That is our interpretation of the different possible indifference curves we have. Well, let's go take a look at the next example. Okay, so here we have a sequential game. This is an example of the ultimatum game. Let's walk through what is happening here, and well, let's read the question to start off. So the figure shows the game tree for an ultimatum game where the proposer has $100 and offers a proportion of it to the responder. The responder can then either accept or reject the offer. If the responder accepts, both the proposer and the responder keep the agreed share. While if the responder rejects, then both of them receive nothing. Read the following statements and select the correct ones. This, just a bit of an aside, is such a fascinating game because when this was first done in experiments, it really confused so many people because it kind of went against what was initially thought to be your basic idea of economics. And let's work through an example to kind of demonstrate that before we go into this specific example. So, say we have the proposer and say that they offer $1 and they keep 99 to themselves. For the responder, should you either accept that and get $1 while the proposer gets 99, or should you reject that and you both get nothing? Well, one of those things where it's like, well, initially, before the proposer offered anything, in fact, the proposer is offering this dollar entirely out of their generosity. You are entirely better off just accepting the $1. But yet, when this was gone through, it was found again and again and again, players were rejecting that offer. Even though they're better off getting $1 than they were at the start. At the start, they both had zero. You're better off. $1 is better than $0. They were continually rejecting. And why? Why were they continually rejecting when they were being given money? Well, the big outcome really comes down to this notion of fairness that we have. And we have this implicitly built into us, this notion, this social norm of fairness and what an acceptable amount of fairness is. And when you are offered an unfair distribution, you will reject it despite yourself if it means also hurting the other person. That is because you are so insulted by this lack of fairness that they would go against this social norm that you will willingly forego this $1 of benefit in order to ensure that they also forego their benefit. And so in this case here, you have a minimum offer that you see as fair, and you would thus have a response function based off of the joy, happiness that you would get from denying the other side their ability to get their return. Okay, that's a bit of background. Let's go and actually talk through this all together. Let me just clean up and then we'll do that. Okay, so we'll get into the comments, but first let's just go through the game flow. This is what we would call a sequential game. That is, we are not both making your choices at the same time. The previous ones we looked at, let's go back, this guy and that guy, these are both simultaneous games. That is, you make your choice simultaneously, or even if you're making them at different times, you're unaware of what choice the other person made. It might as well have been simultaneous. You don't get to choose your action based on what they chose. You just have to make this in uncertainty, not knowing which one they chose. In this case, though, you're doing it sequentially. The responder acts after the proposer does. So the proposer moves first, either does an offer of 50-50 or an offer of 80-20. From here, the responder then responds with what their response would be. So if the proposer offers to split that $100 50-50, the responder can either accept it, they both get $50, or the responder could reject it and they both get zero. Alternatively, the proposer could offer $80 and only keep 20 for themselves. In this case here, actually, I think I'm reading that wrong. Let's see, where's the breakdown here? Where's the breakdown? Does it say? Where the proposer has 100 and offers a proportion of it to the responder, who can either accept or reject the offer. If the responder accepts, the proposer and the responder keep the agreed share, while if the responder rejects, then they receive nothing. Okay, so in this case here, my bad, the 80 is what the proposer keeps, the 20 is what is being offered to the responder. So the offer is, I'll keep 80, I'll give you 20 as the responder. Okay, moving on to the responder. The responder can either accept this, get 20 for themselves, meaning the proposer keeps the 80, or the responder can reject it and they both walk away with zero. Okay, walk through, talk through as to how that game flows through. Let's take a look. First comment, this is a simultaneous game. False. I just said as we introduced this is a sequential game. One player moves, the other player then responds. B, if the proposer offers 50-50, then the responder should accept. I'm going to go right away and say that's false, and you might be like, what? Why, Keith? That's a very fair offer. Yeah, that is a fair offer because of your social norm of fairness, your understanding as to what would be a fair offer. What we have to keep in mind is that the responder would have their response function, what is their minimum acceptable offer, and they get some level of utility from denying the proposer their payoff in the case that it is unfair. So we don't know what the we don't know what the responder's function is here, so we can't be sure. We can't be sure that they would accept. It entirely depends on the responder's function in that case. The worst possible outcome from the proposer is 50. No. The worst possible outcome for the proposer is to receive zero. So that's a false outcome there. Process of elimination, it must then be the fourth one, and that is if the responder's minimum acceptable offer is 21, so that is the lowest offer they would accept is 21, then he attains a higher utility from rejecting rather than accepting the offer of 80-20. Yeah, that's exactly it. The reason why the minimum acceptable offer is 21 is because as soon as the offer goes below that, the responder gets satisfaction from they're so insulted. They feel that is such an unjust offer that they were just given of 20. That is so unjust that the satisfaction they see of denying the proposer $80 more than accounts for that loss of 20 that they would have otherwise had. So in that case there, this is our correct answer, D. I believe what we have coming up next is an example where we work through these minimum acceptable offers, work through that response function, and we can see what I've been talking about in practice. So if you were kind of lost a bit about what I was getting at with response functions, with that minimum acceptable offer, well, let's go jump over. Let's take a look at that one. Okay, so here as we have our the reciprocity motive and their corresponding response function. So let's read the intro and then let's go work through this. So first, consider the ultimatum game. So like we just played. However, we're going to say that the social norm is a 60-40 split. That means that the proposer keeps 60 and the responder receives 40. Social norm, meaning this is what we believe fairness to be. This is like the lower bound of fairness. Let R represent how strong the responder's private reciprocity motive is, such that his satisfaction at rejecting an offer of Y less than 40 is R times 40 minus y. Based on this information, we can conclude that. Okay, bunch of stuff. What we want to get first is our decision rule. So if we have y, let's go like this. If we have y being what we have been offered, if y is less than r, our reciprocity function, that is what the value we place on that, how strong that motive is, then 40 minus y, we get our reject function. That is our decision rule. We would say that, hey, if y, the amount being offered, is less than this bid on the right-hand side, then we reject the offer. If our offer, again, y is the offer, if our offer is greater than the right-hand side, then we accept it. So what is that value of that offer? Well, right now we don't really see that explicitly because we have y on both sides, but we can rearrange this to solve for y to figure out what our minimum acceptable offer is. So a little bit of algebra. Let's go work through it. The way that I would do that is I would first multiply r into the brackets there. So we have y is less than r40, which is then minus ry. That's an ry. Okay. We then want to put y's together, so let's move ry to the other side of the inequality. So we'll add ry to both sides. We get ry plus y is less than r40. Okay, let's bring those y's together. That is just the reverse of what we did here, where we multiplied the r in, and now we had an r attached to both terms. We have a y attached to both terms, so we can take that out, and that would be y r plus 1, and that is less than r40. Finally, let's get y by itself, so let's divide both sides by r plus 1. So we have y is less than r40 all over r plus 1, or 1 plus r, doesn't really matter. We'll go like we have it, r plus 1. I say it doesn't really matter because I just saw up here that they have is 1 plus r, potato, potato. Okay, so what we essentially end up getting from here is that if, this is still the same decision rule, if our offer is less than whatever this right-hand side turns out to be, we reject. So if offer is less than this value, reject. If our offer is greater than this value, or equal to, we will accept. What we want to keep in mind is that this entirely depends on what the value of r is. Entirely depends on what the value of r is. So let's go work through our comments based off of this. The responder will reject any offers below 60r all over 1 plus r. No. We have, again, if we just want to write it in that format, that would be 40r all over 1 plus r. Like I said, potato, potato, because they're being multiplied, being added. Doesn't matter if we go 1 plus r or r plus 1, r40 or 40r. Same mathematical operation, just expressed differently. Okay, so that's false. That's false. If r equals 0, then the responder will reject any offer. Well, wait a minute, that doesn't sound right. Let's take a look. What happens if r equals 0? You have 0 times 40 all over 0 plus 1. So you have 0 over 1 equals 0. So we said our rejection rule was reject if our offer is less than... Oh, wait a minute. That makes no sense at all. How would you have an offer less than 0? You can't. So if r is 0, we will actually accept any offer. So that is false. Because again, this is our rejection rule. We will reject if the offer is less than what this works out to be. So at an R of 0, nah, there's no way we would ever reject. We would always accept. If R equals 1, the minimum rent that the responder requires to accept an offer is 20. Well, let's work that out. Minimum offer, so R is less than, what did we say, R of 1? So 1 times 40 all over 1 plus 1. So 1 times 40 is 40. 1 plus 1 is 2. 20. So if y is less than 20, we will reject. Okay, if y is less than 20, we will reject. So the minimum rent that the responder requires to accept an offer is 20. So in this case here, hey, there we go. There we go. We have that is a true statement. When the value of our reciprocity motive is 1, we would have a minimum acceptable offer of 20. So let's mark that. If R is 1.5, then the maximum rent that the proposer can claim is 76. Well, okay, let's work that guy out. So y of R of 1.5 times 40 all over 1 plus R. So 1 plus 1.5. So what do we get? 1.5 times 40, that's going to be 60 all over 2.5. 60 over 2.5, what does that work out for us? That works out to a value of 24. So if we get an offer less than 24, we reject. If we get an offer greater than or equal to 24, we will accept. So the maximum rent that the proposer can claim is 76. I guarantee you a lot of you are just knee-jerk reaction looking at 76, looking at 24 and saying that's false. We've switched the terms here. We're not talking about the responder anymore, we're talking about the proposer. So, hey, if the proposer were to offer 76, that is that the responder would receive 24. That is for our 100 altogether, right? So in this case here, if R is 1.5, yeah, they could offer you 24. They could claim 76, and you would accept that. This is your minimum willingness to accept based off of your reciprocity motive of 1.5. So that is, in this case here, this is also a correct answer. We got 2 correct answers in this one. So both of those would be correct. Again, the big thing in this is we just need to figure out what is our rejection rule, what is our minimum offer, and working through based off of different reciprocity motives, we can figure out what our minimum price that we would accept is. Let's go carry on. Let's take a look at the next set of examples. Okay, in this one, we have what looks to be a public goods problem. Let's talk through that and what that means. Let's read the intro to start off. Bruce owns a cooperative project with 2 other members. So there's 3 members altogether. Any member that chooses to put in a full day of work faces a cost of £50. That's their cost maybe of getting to work. But they're able to produce a total income of 120. So, okay, you have a cost of showing up, but you get to generate income. Cool. But this income is shared amongst the 3 of you. Okay, so for example, if Bruce and 1 other member do a full day of work, then the income per member is the $120 for each one of them working, times 2, because it's Bruce and 1 other, but then divided by 3 because all the income is shared between all members of the cooperative. So divided by 3 means that they're getting $80 worth of revenue. This leaves Bruce with a net income of that $80 he receives minus the 50 cost to work, gets £30 of net income. Let's assume that a member must either put in a full day or none, so you can't do half days, 3/4, anything like that. It's either on or off. Based on this information, let's read the following statements and select the correct ones. Okay, so what we end up getting then is we get a few different possible outcomes. Let's talk through these. We could re-express this function here as the following. We get 120 times n, the number of people working up to 3, divided by 3. And that there equals the individual income. So that is the individual payoff, the individual income altogether. So for example, if we have, and sorry, I want to be clear, that looks like a plus sign to me right now. That is just saying times n. So if we start off, if we have n of 1, so only Bruce shows up to work, well, we would have 120 times 1 divided by 3. So 120 divided by 3, that's going to be $40 worth of income. If n is 2, well, then we have 120 times 2 divided by 3. Well, that gives us what we just had in the question of 80. And then finally, if we have 120 times 3 divided by 3, let's again, n equals 3. 120 times 3 divided by 3, that gives us 120. Now, keep in mind, that's just our income. If we take a look at our net income, that is after our cost, that is we have a cost of 50 pounds. Well, then our net income, that looks like a T, let's make that more a Y. There we go. Our net income would be our income of 40 minus 50. We would get negative 10. This is the example from the question. There's 30. And then 120 minus 50, that would be 70. So we see that, hey, really, this cooperative only works if we get people to buy in. If you form a cooperative, but then you're the only one doing the work, you're actually losing out altogether. Okay, let's go work through this altogether, see which of these outcomes are correct. So the first one there, the socially optimal outcome, that is the one with the highest total net income, is when everybody works. Well, hey, we just went through that. Yeah, when n equals 3, we get a net income per person of 70. So that is the highest net income. Yeah, that is our first true statement. What do we have? The dominant strategy equilibrium of this public game is when no one works. Okay, well, let's figure this out. Right now, I figured out, hey, what is the payoff, assuming I was the one choosing to work each time? So, hey, if I worked, I got negative 10. If me and somebody else worked, we each got 30. And if all three of us worked, we got 70. So that was if work. So if we worked, we got that payoff. But what would be my payoff if I decide to shirk? That is, if I were to free ride, if I were to say, no, thank you, I don't want to work. In that case, my net income is, well, what's my cost if I'm not working? My cost if I'm not working is 0. So, okay, what should I do? If I don't work, have a 0 cost, I get my income, I have no cost, so I could earn 40. If two people work, well, if two people work, that would be 120 times 2, so 240 split 3 ways, that's $80 each. I don't have any negative cost, so I just get $80 worth of income. Now, mind you, we can't do this one because I can't shirk and have all three people work. So this one is just non-defined. We can't look at that one as a possibility. So, hey, wait a minute. If I am just self-interested, I just want to make sure that I am maximizing my own net income, my own payoff. What ought I to do? Well, payoff between working or shirking, I should shirk. I should not work. I should free ride. If we have two people showing up, what should I do? Should I work or should I free ride? Again, free riding is the better payoff, so I should again free ride. And then keep in mind, what if we all three of us show up? Well, in this case here, I'd still be better off not showing up and getting the 80 than showing up and only getting 70 split three ways. So in this case here, I don't even have an incentive to consider that. Like we said, it's undefined, but I wouldn't want to show up to be the third person because I'm actually earning more free riding and not being there for when there's the two other people working. So in this case here, we actually have a dominant strategy to shirk. That is a dominant strategy to free ride or to not work. What is this? The dominant strategy equilibrium of this public goods game is when no one works. Yeah, this is the problem with public goods. You typically have the incentive to free ride. You have the incentive to hope everybody else does it, and you don't. The third option, Bruce is better off not working, irrespective of the actions of the other members. Yeah, that's what we just showed in the green column here. That could have been for any of the cooperative members, but for Bruce, Bruce is always better off not working than working, so Bruce is going to have a tendency to not work. There we go. What about the final one? Do we have all of these being true? Bruce's net income when all three members work is 80. Nope. When all three members work, the net income is only 70. So, not quite a full sweep. That one is false. Okay, let's go carry on and take a look at some more. Okay, here we are getting into a bit more of this. And let me maybe just readjust a little bit here. I'm thinking this doesn't show up all the way on the screen, but you know what? That might be okay. I'll just scroll down for a second. All that we have showing up in the bottom bit there is just the definitions of what we have for II, IT, TI, and TT. So that is also in the little matrix up there on top. So I don't actually think we need to readjust to make sure we can see that because we'll be okay. So there we go. We'll be fine with something like that. Okay, so what do we have going on? Let's read the intro again. Anil and Bala have the choice of either using the integrated pest control or Terminator to solve the problem of pest insects. The following table shows their payoffs depending on their choice, and the following diagram shows the possible outcomes on a graph. Based on this information, read the following statements and select the correct one. Okay, so I mean, we can go through this and see how we play the game, and then we can take a look to see what are the Pareto efficient points. Do any of the points Pareto dominate another point? And we'll go through all that, and then we'll look at the questions. So first, let's play the game. Let's play the game. Again, I typically start off with the row player. So I'll start off with Anil. And Anil would fix Bala's strategy. So Bala's going IPC. What is Anil's best response? Best response is 4. 4 beats 3. So let's go 4. Then Anil's saying, but what's best response if Bala goes Terminator? Well, if Bala goes Terminator, Anil is looking at a payoff of either 1 or 2. So 2 is the best response there. Anil has a dominant strategy of always playing Terminator. Great. Let's switch it around. Let's now be Bala. And what is Bala going to do if Anil goes IPC? What's Bala's best response? Well, again, we're either looking at a payoff of 3 or 4. 4 is a better payoff, so Bala would go Terminator if Anil goes IPC. And then if Anil goes Terminator, what's Bala's best response? Either 1 or 2. 2 is that best response there. And so what we get is a dominant equilibrium. We have 2 dominant strategies of playing Terminator, Terminator, a dominant equilibrium, a Nash equilibrium at TT. So that is, with this game, where we would end up. Okay. While that is where we would end up in the game as it is, if we were entirely just selfish, self-interested players, let's go work through, hey, which of these are Pareto efficient? Are any of them Pareto inefficient? And do any of them Pareto dominate any of the others? So we've done this already, but let's start off with IT. So there's IT. We have nothing up to the right, so this one is not dominated. Nothing is dominating that strategy, so that is Pareto efficient. Yes, that is a Pareto efficient outcome. No other strategy is dominating it. Then we would have II. If we take a look at II, again, there is no strategies up to the right, so there is no strategies dominating this one. This one, again, is Pareto efficient. And then let's see how this yellow shows up. We have TI that looks barely showing up at all, but hopefully you can see that slightly at TI. At TI, again, nothing up to the right, so nothing dominating that. Again, that one is Pareto efficient. This leaves our last one, our dominant equilibrium, our Nash equilibrium of TT. If we take a look at TT, up to the right, we see that II, that is IPC, is actually an improvement over TT. They are both better off there. That again tells us that the Nash equilibrium, the dominant equilibrium of terminator-terminator, is Pareto inefficient. So I'm going to put an X there for being inefficient. This is a prisoner's dilemma style game, is what this is. Okay, so now that we've gone through that, let's actually read the potential comments and see which one or ones are correct. II is the unique Pareto efficient outcome. No, we've seen that there's 3 Pareto efficient outcomes, IT, II, and TI. So II is not the unique Pareto efficient outcome. What do we have? Anil and Bala can Pareto improve from by moving from TT to TI. So by making that movement there, we're saying, hey, they can Pareto improve. No, Bala would be worse off, right? In this case, sure, Anil goes +2, but Bala is -1. So that is not a Pareto improvement. As I mentioned at the start of this whole video series, is this would be what we would call a potential Pareto improvement, because Anil could compensate Bala for her loss such that no one is worse off, in which case there's the potential for it to be a Pareto improvement, but it is not a Pareto improvement at all. So this guy is also false. Again, false for the first one, false for the second one. What's the third one? Maybe let's just clean up here and then take a look at the third one. Okay, what's the third one? Anil and Bala will both be happy to move from the Pareto efficient IT to the fairer II. So that would be moving from IT to II. Again, no, they would not both be happy to do that because it's not a Pareto improvement. Bala is losing one payoff to do that move, so would not be happy. That is false. The last one here, which by process of elimination must be true, the Nash equilibrium in this game is unique and Pareto dominated by at least one other outcome. Yes, it is unique. We only have one Nash equilibrium right there at terminator-terminator, and this is dominated by IPC. So this is true. Nash equilibrium is unique, and it is Pareto dominated. So we have our correct answer. Well, let's go carry on. We got a few more left. Let's keep burning through these. Okay, we have 4 more, including this one. Let's take a look. We have another one. This time we have Ali and Bilal, and the payoffs of the corresponding allocations. Looks like allocations depending on whether they grow cotton or grow rice. Based on the information, let's read the following statements and select the correct ones. Okay. We have one, two, three, four, five. We have six possible outcomes here, so a little bit, a lot going on. What I maybe want to do, and everything here is talking about Pareto domination, and so we don't actually need to do this, but there are some questions that may pop up where this could be helpful. So I do want to go through and say, hey, this is a possibility of something we can look at. And you'll probably hate me because of this even is a possibility, but let's go take a look. What we have is, okay, we have Ali. Let's say Ali is our row player. What does Ali have? We have C, C, R, R, C, R. Okay, so Ali, let's start off there. Ali has the choice of either C or R, which I'm assuming is either cotton or rice. Okay, we also have Bilal, and Bilal has the option of R, C, R, C, M, M. So Bilal actually has three options available. So has C, R, or M. That is what we can do is from this graph, from all of these points, we can generate a game matrix. And maybe let's just use the line tool instead of trying to freehand that. We'll have a little bit of both. There we go. There we go. What we can do is we can populate this. We have the option of CC. Well, just taking a look for CC there. That is going to be Ali with a payoff of 3, Bilal 5. So 3, comma 5. We have, again, what I want you to keep in mind is the way that we're reading this is X, comma Y. So R, comma C. Where do we have R, comma C? Right here. So that is 5, comma 6. We then have C, comma R. Where's C, comma R? That's right here. That's going to be 3, comma 6. We then have R, comma R. R, comma R is right here. That's 4, comma 4. And then we are going to have C, comma M. That's up in the top right there. That's 6, 7. And we have R, comma M. R, comma M is right below that one, and that is 6, comma 5. So the reason why I wanted to do that was to showcase that, yes, we have all of our payoffs being placed as such, which is sometimes great because we get to see the Pareto outcome, Pareto efficiency, what Pareto dominates what a lot easier. But it's much more difficult to actually play the game and figure out where a Nash equilibrium would be. Now, the question doesn't ask anything about Nash equilibriums. It doesn't ask anything about dominant strategies. So in this context, this is a moot point. But I did want to showcase this as there are other questions that pop up that do ask this. And you need to be able to build that matrix from the payoff graph. Since we have it, let's just quickly play the game, see if there's a dominant strategy, see if there's a Nash equilibrium, and see where that winds up. Again, no rhyme or reason. I typically start off with the row player. So starting off with Ali, if Bilal fixes to grow cotton, what's Ali's best response? 3 or 5? I'm going to go with 5. If Bilal fixes to go with rice, what's Ali's best response? 3 or 4? I'm going to go with 4. If Bilal goes and grows maize, that is corn, what is Ali's best response? Ali's indifferent. They both give us the same payoff of 6. So in this case here, Ali is always picking rice, except when we have maize, in which case Ali doesn't care. We'll go and switch to corn. We then have Bilal. Let's see what Bilal's doing. If Ali picks corn, sorry, C is not corn. C is, what was C? Cotton. My apologies. Maize was corn. Wow, I'm messing myself up. Okay. If Ali picks cotton, what is Bilal's best response? 5, 6, or 7? Definitely 7. And if Ali picks rice, what is Bilal's best response? 6, 4, or 5? We have 6. So in this case, we actually see there's two Nash equilibriums at rice cotton. Where is that? That is right there, is one of those Nash equilibriums. That is, I used blue for that one. The other Nash equilibrium is at cotton maize, which is this one here. Interesting. We have two Nash equilibriums, both stable, where we could end up. However, hopefully that pops out at you. One of them is Pareto dominated by the other. One of those outcomes is Pareto inefficient. Let's go work through the potential comments and see if we can identify the correct ones. Okay, the allocation at CM, Pareto dominates RC. Yeah, that is exactly the case. And right, we can see that. Here is RC. Let's keep our colors consistent. There's RC. We see that CM is higher payoff for both parties, so CM is entirely Pareto dominating RC. So RC is Pareto inefficient. Big X there, inefficient. Okay, so that is correct. The Nash equilibrium is Pareto efficient. I struggle with this wording. I would say a Nash equilibrium is Pareto efficient because, as we've just talked about, there are more than one Nash equilibrium. So one of those Nash equilibriums is Pareto inefficient. I don't love the wording of that question because it's just referring to the, as in there's only one. We've gone and we've identified that there's actually two Nash equilibria. So no, I'm going to say that this is false, just because I'm going to be a bit semantic with that, and given this question set, often they are rather nitpicky with the wording. So I'm going to say that guy's false. The third option here, the allocation RR is Pareto dominated by RC and CM. Well, let's take a look. We'll use red for that. Here's RR. Yes, it is dominated by RC. That's that guy. Yes, it's dominated by CM. That's that guy. But it's also Pareto dominated by RM. So this isn't entirely true. Because it's not entirely true, I'm going to go and say that that is false. Fourth one, there is only one Pareto efficient allocation. And to be clear, the reason why this is false is because it's not entirely true. There's another one here, RM, which is also Pareto dominating RR. Okay, let's go back to 4. There is only one Pareto efficient allocation. So again, a Pareto efficient allocation is one that has nothing Pareto dominating it. What do we have? Well, we've already ruled out RC as being Pareto efficient. We've ruled out RR as being Pareto efficient. RM, I could rule out RM as well. How can you do that, Keith? Well, because again, if I just go up, we see that CM, no one is worse off, but somebody is better off. So CM Pareto dominates RM. In the same way, if we take a look here, CC is Pareto dominated by CR. CC is Pareto dominated by RM. And then what about CR there? Well, CR is Pareto dominated by both RC and CM. So as we went through this, Pareto inefficient, Pareto inefficient, Pareto inefficient, Pareto inefficient. We only actually have one outcome, which is Pareto efficient, and that is CM. Everything else is Pareto dominated by something else. So yes, there is only one Pareto efficient allocation in this payoff matrix here. Finally, the allocation RR. Maybe let me just erase some stuff here so I can see where RR is. There we go. Okay, so the allocation RR is better than CC based on the Pareto criterion. No, because we can't get to RR without Bilal being worse off. So that's not true. That is not a Pareto improvement. So our answers are the first one and the fourth one. Those guys are correct. The rest are false. Hopefully that helped into how to work through this. And I was wrong. We did actually. It was helpful to know the Nash equilibrium in our ability to answer the second one there correctly. So this wasn't all in vain to go through that. Let's go take a look. We should have 3 more left in this video. Okay, so a bunch of information here. I've plopped it out on 2 different parts so we can see it all. We have Ronnie and Lizzie, who are elementary school math teachers with adjacent classrooms. Uh-oh. Both like to teach math through group activities that involve teamwork and moving around in the classroom. That's an exciting way to teach math. While this causes noise enough to disturb the other's class, they continue to use activities to teach math as the kids love them. The payoff matrix shows the satisfaction each attains from lessons taught, with and without the use of activities. The allocations are represented to the payoff matrix, labeled A, B, C, and D, that is to the right there on the graph, have been plotted in the graph with Lizzie's payoff on the horizontal and Ronnie's on the vertical, based on the information which of the ones are correct. Okay, again, let's just play the game to start off. Many of these games we've looked at so far have been like 4, 4. In this case, we have this diagonal line. The first one goes to Lizzie, the second one goes to Ronnie. Just like as if there's a comma, they just have the diagonal line as a separate way of doing it. Okay, so to play the game first, let's start off. Again, no rhyme or reason. I just start with the row player. So let's start with Lizzie, and let's lock in Ronnie's strategy. So if Ronnie does with activities, Lizzie could either do with or without. With is that better payoff. So if Ronnie does activities, Lizzie does activities. If Ronnie goes without activities, though, Lizzie will go, well, we could get either a payoff of 3 or a payoff of 1. Again, 3 looks like the better payoff there to me. So we have Lizzie always going with activities. That is going to be Lizzie's best response always. Lizzie has a dominant strategy. What about Ronnie? What does Ronnie do? Well, let's start off by presuming that Lizzie fixes her strategy with her dominant strategy of activities. Ronnie can either get 4 or 2. 4 is the better one there. So we have a Nash equilibrium of activity, activity. What does Ronnie do if Lizzie goes no activities, though? Well, can either get 5 or 1. 5 would be the better one there. So again, Ronnie has a dominant strategy. That dominant strategy is with activities. As a result, we have a dominant equilibrium. I'll do that in green. That is also our Nash equilibrium, which is activities, activities. 4, 4, where is that? That is that guy there. That is our 4, 4. Okay. Let's now go work through our potential comments and figure out which one is correct, which one's true. So we have allocation C is better than allocation D. Okay, let's take a look. C is right here, saying C is better than D. Well, it's not a Pareto improvement. With C, yeah, Ronnie's better off. Ronnie's getting +1, but Lizzie is worse off. Lizzie is getting -2. This isn't even a potential Pareto improvement. You couldn't compensate Lizzie for her loss and be no worse off. So, no, based on the Pareto criterion, C is not better than D. So, no, definitely not the first one there. B, Pareto dominates A. Yeah, that looks correct to me just by eyeballing it. And again, let's take a look and confirm that. I'll use I'll use red. So we're saying B dominates A. So if we go up from A, there we go. In fact, B, C, and D all dominate A. So yeah, that's a true statement. Pareto C dominates over B? Well, C over B. So again, if we look at B, well, in this case, no, that's not the case. C is up to the left there, not up to the right. The only one that dominates B is D. So no, that's a false statement. C does not Pareto dominate over B. What do we have for our fourth one? Allocation A is not Pareto dominated by any allocation. We just disproved that. We just said allocation B dominates A, so that can't be true. That's false. Allocation D is Pareto dominating over all other allocations. My knee jerk was to say yes, but as soon as I looked at that diagram, I realized that that is wrong. And that is, why is that wrong? We know that D dominates B. We know D dominates A. But if we take a look at C here, D does not dominate C. So both of these, both C and D are Pareto efficient. So the only correct one in this case, the only correct one is our second one, that allocation B dominates A. That's all we can say for true with this statement here. Let's go take a look, about two more left. Okay, here we are back to Anil and Bala with their choice as to which kind of pest control to use, and just a bit of a different way of looking at this, I suppose. So Anil and Bala have the choice of using either the IPC or Terminator to solve the problem of pest insects. The table below shows their payoffs depending on their choice, and the diagram to the right shows the possible outcomes on the graph. Based on the information, which of the ones are correct? Okay. We've played this game, we know the outcome, and we kind of have all the dominated and dominating strategies shown over there on the right. But let's just quickly identify our Nash equilibrium, any potential dominant equilibriums, just to start us off and ensure we're on the right track. So again, let's start off. With Anil. And what is Anil going to do if Bala chooses IPC? Well, Anil is choosing between 3 and 4. 4 is going to be that better payoff. That's what Anil will choose. What's Anil's best response if Bala chooses Terminator? Well, between 1 and 2, 2 is the better one there, so Anil will again choose Terminator. Switch the game around, we'll now play as Bala. If Anil chooses IPC, what does Bala choose, 3 or 4? 4 is the better payoff, so we'll go that route. And if Anil chooses Terminator, what is Bala's best response, 1 or 2? 2 is the better response there. So we get our Nash equilibrium, which, hey, they both also have dominant strategies, so it's also our dominant equilibrium. Great. And let's do that in, I don't know, this brown color to showcase that. That is TT. That is that guy there. That's our Nash equilibrium. Okay, what do we have for true comments? II is the unique Pareto efficient outcome. I feel like we've done this already. No, this is not true. To be Pareto efficient, the only kind of criteria to be Pareto efficient is to not be Pareto dominated by any other one. And in this case here, yeah, nothing dominates II, but nothing dominates IT. Nothing dominates TI. So we actually have 3 Pareto efficient outcomes as such. So no, that's false. It is not the unique Pareto efficient outcome. We have TI Pareto dominates TT. No, TI does not Pareto dominate TT. TI would have to be up at least 1 payoff for Bilal for that to be true. So this guy is false. Option 3, TT is the only Pareto inefficient outcome. Yeah, that's a true statement. TT is the only Pareto inefficient because the other 3 are Pareto efficient. This is the only one that's being dominated. It's the only one that is inefficient. Finally, Anil and Bala will both be happy to move from the Pareto efficient IT to the fairer II. No, they would not be happy to make that move. And the reason is sure, Anil might be. Anil gets +2 going from there to there. But Bilal is not happy, -1. Again, this is a potential Pareto improvement. Anil could compensate Bilal, but on its own would not be happy to make that move. So we only have that one as the correct answer here. Let's go take a look, I believe, at our final question. Okay, here is the final one, leaving this one for last as it's getting into the most difficult, fun aspects of it, and that's where we are dealing with both our payoff matrices, Pareto domination, the Pareto criterion, as well as we're throwing in these indifference curves and whether we are completely selfish or altruistic, and that's going to change our potential outcomes here. That being said, let's read this lengthy intro. Let's play the game. Let's identify if we have any Pareto domination, Pareto efficient points, inefficient points, and the rest. And then we'll jump over to the comments and see what we can pick through. So let's start off, and my apologies, I'm taking a look at that matrix and it looks pretty fuzzy to me even. I'll try to talk through, maybe try to make those numbers a bit bigger. Actually, maybe let me just do that right now, see if I can make that a little bit more clearer for us before we get started. Okay, I've spliced that matrix to make it a bit bigger. Hopefully that makes it a bit clearer. It's still a little fuzzy, but I think it's more readable now. Let's read the intro and then get going. So we have Paul and Alice, who can be considered representative of two groups of people. They each have two options to commute to work in the city. They can either use their own combustion-powered car, which, yes, allows them to move quickly and gives them slightly more time each day, although this activity also contributes to environmental degradation. Alternatively, they could cycle. While cycling it results in less pollution and is more environmentally friendly means of transport, it actually entails a longer journey time and somewhat more personal risk. That is an infrastructure problem due to the city's lack of investment in that. Sorry, that was an aside comment. The right side of the figure shows the payoff matrix for each of the options in the simultaneous one-shot game. On the left-hand side is Alice's altruistic preferences, and those are represented by her indifference curves. Together with the combinations of decisions she can make, let's assume that Paul's decision is to use his combustion car. Based on this information, read the following statements and select the correct ones. Okay, so we kind of just know Paul, no matter what, is choosing his car. So we can almost eliminate Paul having the option to cycle, but let's still play the game in full as if we don't know that. I mean, that might be Paul's dominant strategy. That might be why. So let's take a look. Let's start off, again, we'll start off with Alice. So if Paul cycles, which we've already said he won't, what is Alice's best response? If Paul cycles, well, either bicycle or combustion. That's bicycling is a payoff of 4. Driving the car, payoff of 5. 5 wins out. If Paul takes the car, which is what it says Paul would do, what is Alice's best response? Either cycle for 2 or drive herself for 3. Driving herself for 3 is the best response there. Alice has a dominant strategy to always drive. Again, while we said Paul will always choose the car, let's actually work out Paul's best responses. We'll do blue for that. If Alice cycles, what is Paul's best response? Either 4 or 5. 5 for driving is better for Paul, so that's what Paul chooses. And then if we go Alice choosing the combustion car, what's best, 2 or 3? Again, 3. Paul also has a dominant strategy to always drive, and we get our Nash equilibrium of 3, 3 of car. That is on our graph right there. Okay. Based off of this, just taking a look at the indifference curves, we can, just to interpret this, although B, C, and C, C are, we can't say one Pareto dominates the other. From Alice's perspective, No, I'm going to take that back. I thought they were both on the same indifference curve, meaning she would be indifferent between those two outcomes. But as I look closer here, let's zoom in. CC is actually below that indifference curve, meaning no, she would not be indifferent between those two options. It's just slightly below. So, never mind. I take that back. That statement I was going to make. Let's reset here. Okay, now that we are reset, what do we have for any Pareto domination and the rest? Let's start with CC, where we end up. That is our Nash equilibrium and our dominant equilibrium. And we kind of have our prisoner's dilemma case where we end up is not Pareto efficient because it is Pareto dominated by bike. Bike is the socially optimal outcome, but not where we end up. Bike is Pareto efficient because nothing dominates it. So that guy is Pareto efficient. And on our highest indifference curve, CB, that is Alice drives her car, Paul bikes. Where does that put us? That puts us something like that. Again, nothing Pareto dominates it, so that is Pareto efficient. Uh, Keep in mind, with relation to car, even with Alice driving and Paul taking a bike, this point is actually a higher level of utility, a higher happiness than our Nash equilibrium. Finally, we have Alice biking and Paul driving. In that case there, which colors do I have left? I'm running out of colors. Maybe I'll just have to use red again for this one. There we go. Again, nothing is Pareto dominating this, so that is Pareto efficient. And with what we saw when we zoomed in there, this indifference curve that BC is on is actually slightly higher than CC, meaning that, well, she would actually be happier at that point than the Nash equilibrium based off of her indifference functions. Okay, well, that being said, we've taken a look at all that. Let's go take a look at our comments and figure out which one's true. So first, Alice's best response is to use the bicycle because it is the option that provides her with the greatest utility as it is constrained by the most distant utility curve. So unfortunately, that is not the case because Alice cannot force Paul to cooperate. Now, if Alice could force Paul to cooperate and also bike, well then, yes, they could end up at that bike. But at this point here, right, I'm really focusing on that point, is it's constrained by the most distant indifferent curve. That would be the BB outcome. We can't force Paul to bike. So no, that is not the best response. What do we have for our second option? Second option here is Alice's best response is to use the bicycle because she is also valuing the benefits that commuting by bicycle can have for Paul. Okay, this is where maybe this is a bit lost on us. Taking a look at the game matrix, you're like, no, Alice is always choosing car. Well, yes, just based off of this selfish outlay of Alice only caring about Alice, yes, Alice will always choose car. But in this case here, Alice gets to choose between car and bike, given that Paul always chooses car, right? A, because that is Paul's dominant strategy. B, because we said that up here in the intro, so we can ignore these 2 points as being non-existent, meaning that Alice is choosing between, let's just zoom in here to really demonstrate this. Alice is choosing between drive, which is below that indifference curve, or Alice bikes while Paul drives, which is on that indifference curve that is up to the right. So there is actually higher levels of happiness, higher utility, much happier there than there would be at CC. So CC, sad. There we go. So higher levels of happiness, higher indifference curve. This would be where she would want to be if Paul for sure is driving. If Paul is definitely driving, in this case, we're going to end up at that, which again, just to reset quickly, is contrary to the completely selfish outcome, that is, where she only cares about herself with the combustion car. Because she is slightly altruistic and has these upward sloping, I guess downward sloping indifference curves, we get that separate, different option. So that is, I'm going to say this guy's true. 3, Alice's best response is to use her car because she will derive more utility from the direct use of that mode than commuting by bicycle. Well, we just took a look. CC is actually below that indifference curve. Because it's below that indifference curve, she'd be better off taking her bike. So, no, that guy's false as well. Alice's, let me try that again, decision will be based solely on purely selfish criteria because this is not a cooperative game. No, not at all, because we said Alice is altruistic. She cares about Paul's utility. It's why the utility function is downward sloping and not just a vertical line. So in this case, our only true one is B. What I want to demonstrate just very, very quickly would be an alternative to this, and that would be the case where Alice is just purely selfish. And I just want to do this because this is the first one we've taken a look at with indifference curves and also the last example that I'm going through. So just to compare and contrast what we've been implicitly doing behind the scenes in all the other ones. So let's go take a look at that. And let me just draw our diagram as we would have had it there. So we have Paul's utility and we have Alice's utility. We have our following points. We'll go that this is BB. We'll go and say that that one is the CB. I'm just trying to recreate that graph on the left. We have that guy there. And then finally, we have car, which is something like that. Okay. So again, car. This is bike car. We have car bike. And we have bike. Okay. In this scenario here, let's say that Alice is purely selfish. So if we have a purely selfish Alice, the indifference curves would be vertical lines. So just like that would be the indifference curve going through BB, going through CB, going through car, and going through bike car. So what I want to demonstrate in this case, and you can imagine, right, these continue upwards too. I just only drew them from the point down, but they would just extend to positive, negative infinity in each direction. Again, with these indifference curves, with this is as you move out to the right or up to the right, you are getting higher and higher levels of utility. As you are moving down to the left, you are getting lower and lower levels of utility. If Alice only cares about Alice, Alice's highest possible utility is when Alice drives and Paul bikes. Just strictly from a selfish perspective, that's what Alice wants. Alice wants everybody else to bike. I mean, that way there, everybody else is not polluting by everybody else biking, all the traffic and congestion's freed up. But Alice gets the freedom to the ease of commuting by car. So from that perspective, Alice's ideal world is everybody else rides their bike and Alice drives her car. Foregoing that, the next best would be this bike scenario, then the car scenario, and the worst possible utility for her, if she is completely selfish, is her biking when everybody else drives. That is the worst outcome because she has to have the longer commute, the difficulty with that, being out in the elements, all the rest, and everybody else is driving, which is just adding to pollution and adding to her danger in being on a bike. So lowest utility altogether. Just wanted to go through that because that's a very distinct difference from what we had here, where we had those downward sloping indifference curves. That is where she cared about Paul's utility as well. And depending on that level of altruism, we can get different outcomes. And let me just show you one case. We won't go back to this one because I don't feel it's super clear, but let's just take a look at another, and I'll just clean up and we'll take a look at some altruistic indifference curves instead. So let's start off with our bike. Say we have a situation like that. So some altruistic indifference curve such that there's the trade-off between. There we go. These have to be parallel to each other, and I'm doing my best to try to make that the case, given that I'm just freehanding. Again, these should be parallel lines. I know they're not perfect, but trying my best. And that is because one of our things is indifference curves can never cross each other. Okay, so if we had this level of altruism, that is where Alice cares not just about her benefits, but also cares about Paul's. Well, again, as we move up to the right, we have higher levels of happiness. So in this case, this would be the lowest level of happiness, and this would be the highest level of happiness. And so BB would be where we'd ideally want to be. But if we have the case where, like we said, Paul is always taking the car, well, then we're between this option and that option, right? Paul being the second one, always taking the car. Which one gives me the most happiness? The green line or the yellow line? Well, the green line is giving me more happiness. So if I'm altruistic, I'm going to pick that outcome. Which, again, keep in mind, that was the least favorable outcome if I was entirely selfish. So our outcomes do change based off of our level of altruism, based off of our utility when we play these games. Up until this point, we were just presuming we were entirely selfish. We had no care for the other person at all. We know that in reality, we're not quite that bad. And so we get these off kind of outcomes such that we may end up something like this here, even though it would not be a Nash equilibrium. It would be kind of our happiness maximizing point given what the other player is doing. And that is given that Paul will always drive a car. What does that do for society? Well, here, social payoff is 3 and 3 is 6. Here, we get to increase social payoff to 7. We don't quite get all the way to the highest, which is 8, but we are doing better. So for the altruistic people who care about that, this is where we would end up. Okay, a whole lot of game theory, a whole lot of questions that we went through. Again, if I made a mistake somewhere, that happens as I get excited and work through. I might say one thing, meant another. I might have written one thing that was just my mind going somewhere else. Please comment below. I can put in corrections after the fact. If you have any questions, any parts that just didn't make sense, would like me to recover or further explanation, again, throw in a comment or send me an email, and I can do what I can to answer. Thanks. Till next time.